Welcome back, everyone. So as you can see, it's going to be a good day because we're doing the rules of inference. We all knew it was coming. We're in a new form of logic, new rules of inference. But before we do that, something that I neglected to mention last time was our connective for and. This entire time we've been using dots. Yep. This entire time we've been using dots, and that's all good and well. But for modal logic, what we'll use is what looks like a caret. It looks like the wedge for disjunction, but upside down. This is our new connective for conjunction. So if you see me draw that caret, it just means and. It's just like using the dot. Now that I got that out of the way, let's talk about our rules of inference. First, what we're going to need to know is that these rules of inference will be used for a tree method. We're going to draw trees again, so it's going to be a really good day. And we need to know how our trees look in modal logic, because we don't have just formula anymore. Now we also have worlds in which these formula are either true or false. So at every node of our tree, what we'll have is we'll have some formula A, comma, I, where I is some number from the set of natural numbers. And natural numbers are 0, 1, 2, 3, so on, right? So we'll have our formula A, and then our natural number I representing the numbered world in which A is the case, or not A, or whatever it may be is the case. So there's that. If we don't have that at a node, what we will have is something that looks like this. I, R, J. And again, I and J, they'll come from the set of natural numbers, 1, 2, 3, etc. You get it? And this will be telling us how our worlds will relate to each other, right? So for example, you might say 0, R1. That tells us that 0 accesses 1, or 1 is accessible from 0. So remember, we drew like these arrows to represent it. 0 accesses 1. So that's what IRJ will mean for our nodes. Now, the rules for our connectives are going to be the same as we would expect them from our non-modal logics. The only difference is that the world in which these formula are either true or false will stay attached to these, right? So for example, if I say A or B in the world I, right? And you know what? Let's just make that a number. Just say A or B. No, let's keep it general. A or B and I. Previously, what we would do is we would draw two branches and say A or B. The only difference? We're keeping the world attached. So we'll say A and I or B and I. So if we have A and B and I, guess what? The branch will go down and we'll just say A and I, B and I. So everything is going to follow as you would expect from everything that we've learned with trees. We just now also have these worlds attached with them. And don't forget the commas to separate them like I continuously do. So now we have 4 new rules that come with these modal operators that we saw last time, our square and our diamond, right? So last time we talked about not square A in the world I, and we also talked about not diamond A in the world I. And we now know that what these are going to turn into is we've pushed the tilde through and changed the quote-unquote quantifier, not really quantifiers, to diamond, not A, and I. And then this one goes to diamond, to square, not A and I. And last time we spoke through the logic of why these would be true. So if you haven't seen last video, I would recommend checking that first before continuing with this video. So those are 2 of our rules, but we have 2 more. If we have the case square A, I, and then we see I relates to J, what we can infer from this is that A is true in J. Now let's remember, what does square A even mean for the world I? It means that in every world that I accesses, A is true in those worlds. So if we have square A and I, and we know that I relates to J, then we know that A is true in J. So now what about with our diamond? Well, if we have diamond A and I, well, we can then assume, right? Diamond A and I means that there is some world that I accesses in which A is true. What we do is we then name that world. We say I relates to J, and then we say that A is true in J. Now, there's one restriction with this rule. Do you remember with, I think it was existential instantiation, or even universal instantiation? When we instantiated to a constant, we always instantiated to a new constant. We saw that there could be troubles and that it really just wouldn't be true for us to instantiate to a constant that had already been introduced previously. Likewise, when we have this diamond A, I, and then we name the world J to which I relates, J has to be a world that has not previously occurred on our branch. So that's the one restriction. When we do this rule with the diamond, we have to, I'm going to use the word instantiate, J to a world number that has not yet appeared on the branch in which IRJ will appear. That's the restriction. So now that we've got our rules out of the way, let's draw a tree. And we're just going to do one tree because, we've done trees over and over again. The rules aren't really changing that much. We're going to get some practice with these new rules of inference, but I think if you're confident with trees up to this point, you'll be pretty good moving forward. So let us draw a tree. Okay, so what will my premises and my conclusion be? So my premise, let's say our premise is square, if A then B, and square, if B then C. And we want to say that this will syntactically entail square, if A then C. And I think this should be true. This is a classic example. This is a hypothetical syllogism, something we worked with so long ago. Why did I draw the horseshoe wrong? This will be true. And how do we know that if this is true? Well, as we did, if sigma is our set of premises, right, we write out our premises. So in this case, we have one for our tree. So we'll say square, if A, then B, and square, if A, then C. Then we do not our conclusion. So we negate our conclusion. So we negate square, A, then C. If this tree closes, then our original claim, blah, 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 syntactically entails blah, 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 is true. Now, here is the really important thing. We currently do not have any worlds. That's where things change. So what we do is we just start off by assigning our premise and our conclusion to a world. And that world will start with 0. So now we argue as we would, and a branch will close if we have something of the form A in world I and not A in world I on the same branch. So the only thing that we can do, well, not the only thing, but the first thing I see we can do right now is work on our premise, our conjunction up there, right? So let's just write those individually on one branch. So we'll say square A then B in 0, and we'll say square A then C in 0. And then let's just take a note of that, say, okay, we're done with that one. Okay, what's the next thing we can do? Well, we can change our quote-unquote our quantifier. We can negate the square and put diamond, not if A then C in 0. So let's do that. So we'll have diamond, not if A then C in 0. Okay, we're done with that one. So now what we can do is do our rule of inference for diamond. We can introduce a new world to which 0 will relate, and then make not if A then C true in that world. So 0 is the only number that has appeared so far on this branch, so I'm going to just introduce the number 1. I'll say 0 relates to 1, and we are quickly running out of room for this tree. And then what I'll say is not if A then C in the world 1. Okay, cool. So we're done with that rule. Now that we have introduced 0 relating to 1, we can work on our square statements, right? Again, the square, if A then B in 0, means that A then B is true in all worlds to which 0 relates. 0 now relates to 1, so we can make those true in the world 1. So we'll have A then B in world 1, and A then C in world 1. And we're almost out of room, but I know how this ends, so I know it's going to end soon. Okay, so what we have to do now, our not A then C, right? What is the rule of inference for that? Well, A then C becomes not A or C, and then if we negate that by the Morgans, we'll have A and not C. Man, we really are running out of room. So we have A in 1 and not C in 1. So we are done with that. Now, what can we do? Oh gosh, this is getting really, really claustrophobic. Well, the next thing that we could do is we have A then B in 1, and we also have A then C in 1. So with A, oh my gosh, so with A then B in 1, that will become not A or B, not A in 1 or B in 1. So let us write that out. Okay, so we're going to move this tree. This is about to be very wonky. I'm going to draw a branch that goes like up here and then another branch that goes right here. So we'll have not A. Oop, that just moved. So we'll have not A in 1, not A in the world 1, or B in 1. And I just noticed a mistake all the way up here at the beginning. I wrote if A then C. That's supposed to be if B then C. So let's correct that everywhere it appears. So that's A then B. This is supposed to be B then C. Oop, B then C. And likewise, this right here should be B then C. Okay, there we go. So on the branch to our left right here, we have not A in 1, and we also have A in 1. So this branch is going to close. So now we only have to look at the right side. So we have B is true in 1. So the next thing I'm going to do is apply my rule of inference to B then C in 1. And that's going to be not B in 1 or C in 1. So we have not B in 1, which as you could see, immediately causes the branch to close. And then we have or C in 1. Now if we backtrack our branch this way, as you could see, there's a not C and a C in 1. So this branch closes, there's nothing left we can do, the entire tree closed, therefore our original statement at the top, our premises will syntactically entail the conclusion. So, sorry for running out of room at the bottom and also doing a little typo, but I hope that didn't really mess anyone up so far. For the next video, what we'll do is we'll look at how to make a counter model. So when we have an open branch, we'll see the counter model for our claim. It won't be too difficult, nothing crazy. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.